Thanks very much.
Thanks to the organizers for letting me talk about our results today. So my talk is actually, it's going to be on what I'm calling currently main non-directional dichroism. And you'll see in this talk that actually I'm kind of struggling to find kind of a correct terminology with this to describe the effect we see with neutrons. But what I'm really talking about, okay. Thanks. Oh yeah. Okay. But really, this talk is geared at looking at magnetic excitations using neutron scattering in a magnetic field. Now, I'd first like to acknowledge our broad collaboration in this. This is actually involving a number of different neutron facilities, mostly because the sample environment behind these neutron experiments are kind of non-trivial. So we had to go to a number of different places to actually do these experiments. So first of all, this is a collaboration involving Rutgers, Oxford, and also us up in Edinburgh and Glasgow. And we've been working with a number of people at facilities, particularly in Europe and also in the United States at NIST. This is the outline of my talk today. So there's kind of three things that I want to go through here. First is I want to talk about, just first of all, the magnetic and crystallographic structure. I'm going to run through this kind of quickly just because of time constraints. This material is called langocyte. And then second, I'm just going to go over what the spin excitations look like in zero magnetic field. And then the last bit of my talk, I'm going to talk about basically what happens when you apply a symmetry breaking magnetic field to them. And in particular, show you some of the interesting effects that you get when you swap momentum, or the sign of the momentum transfer, or also the sign of the magnetic field. And this is what we're calling directional dichroism in this material. All right, now what are we basically after in these experiments, and what's the point of this? First of all, what we're after is basically to break this. What I'm showing here is something that these neutron scatters, and I think optics people call it sometimes a little bit differently, but anyways, in terms of neutron scattering and magnetism, this is what we call reciprocity. What I mean by this is that an excitation that can be a charged spin wave or a phonon that travels in one direction is actually the same if you reverse the position and the time. So it's the same, so motion in one direction is the same as motion in the opposite direction. And in terms of electronic circuits, there are a lot of devices. This is kind of a simple one, a diode that basically breaks this, where you actually break this kind of symmetry so that the charge flowing in one direction is not the same as it goes the other. And really what the point is of these experiments that I'm going to be talking about is if we can actually devise a way to do this, but instead of with electric charge, but with magnetic excitation, so with spin waves. Now, to actually devise a way that you can possibly do this, I think it's useful to think about kind of the symmetry operations that force this reciprocity. In particular, there's kind of two symmetry operations that I think are important. One is, of course, time reversal symmetry. So if you swap time, you reverse the sign on the momentum transfer, Q. And the other one that comes into play is also position. So I'm calling the inversion operator, and that swaps sign on position. This is kind of played out if you look at Bloch's theorem. You see with Bloch's theorem that if you kind of switch the position with inversion or parity, and also time reversal, you see that you end up with this symmetry here, that the periodic part has to be same if you swap k and you swap r, so that this up here, this exponential takes care of itself. And that's kind of a statement of reciprocity. In terms of kind of local magnetism, I think this is also basically a statement of Kramer's theorem, which the time reversal symmetry actually brings in some sort of degeneracy to your system. Okay, the particular system that we're looking at to see if we can actually break reciprocity with the spin excitations is actually this character here. This has kind of a long chemical formula, but it's called langocyte. It's based on this mineral langocyte. And what I'm plotting out here is the crystallographic structure, but only for iron. It's the magnetic site, it's iron 3+. and the oxygen here. So what I've done, this is got this hexagonal P321 structure, and I plotted the structure here, what it looks like in the AB plane, and also what it looks like along the C direction. And the kind of pinkish red atoms here are the magnetic iron 3 plus sites, and the small blue ones are actually the oxygen. So the structure within the AB plane is based upon these trimers of magnetic iron 3 plus, and they're linked to each other by 2 oxygen atoms. And they form this kind of hexagonal arrangement within the AB plane. Now, what's kind of interesting, I think rather fun about the structure is if you look what happens as you start stacking these things along C. So if you take one trimer and then come out of the plane along the C-axis, you end up with this kind of arrangement here. Now, remember, these are the oxygen atoms. So what's, I think, kind of fascinating about the structure is that the coordination actually has this chiral, it's almost like DNA structure to it, where it has this kind of twist that goes up. And so this structure is actually chiral in itself. And then we can write down the symmetry elements behind it here. Okay, that's what the structure looks like in terms of the iron and the oxygen. Now, the magnetism behind it in terms of how these iron 3 plus sites actually talk to each other is somewhat complicated. Unfortunately, I think a minimal model, unfortunately, requires 5 exchange constants. Within the AB plane, what you have is 2 exchange constants that I think you need to really think about. One is the coupling, of course, within one of these individual trimers. And then one, which is being called J2, about how one trimer talks to the other within the AB plane. What's really important for the purposes of this talk is what happens as you go along C. In that case, because of the chiral nature, you need 3 exchange constants. One to take into account nearest neighbor coupling, so one iron directly above. But if you go out to the next nearest, now it's a bit hard to see with this picture, but if you go to the next nearest neighbor interaction, it turns out there's 2 different oxygen pathways you can take to get there. So that's why you actually need 2 more exchange constants. It's because of the chiral nature of this underlying magnetic structure, the nuclear structure. The magnetism, the actual static magnetic structure behind this, so this thing orders antiferromagnetically at around 27 or 28 Kelvin. And it also has kind of a single-handed chiral magnetic structure as well. And this was first done by Virginie's group in Grenoble. And basically, there's kind of 2 handinesses I think you need to worry about in terms of the magnetic structure. One is how these spins stack as you go along C. And so that's being referred to as the helicity. So as you go from one trimer to the other, the spins adopt a twist associated with that. And also how the magnetic spins are oriented within an individual trimer. And that's being called the chirality. So there's these kind of 2 kind of handinesses that you need to worry about. In terms of how the magnetic spins stack along the C-axis, you can actually understand that in terms of just looking at the exchange constants. This is the classical energy for a given set of exchange constants as you go along C. And you can actually derive these, so we actually initially tried to derive them from inelastic neutrons using some rules. Jens Jensen wrote a really nice theory looking at the individual trimers and writing out kind of the full Green's functions approach for the spin excitations. And it was kind of satisfying that that approach and actually ours, just using some rules, actually gave fairly, I think, consistent results for the exchange constants. But you can see here, this kind of makes sense. So the biggest exchange constant is the one within the trimer. That's called J1, so that's the one that couples one iron to the other. And then the next kind of biggest one along C is this nearest neighbor exchange constant, J3. Now keep in mind, these are of the order of about half to 1 millivolt. That's kind of an important energy scale that we'll have to talk about in a few seconds. It's also kind of satisfying about the analysis that if you compare it to thermodynamic data, actually you get very good agreement with experimental results, and also the ordering wave vector. Okay, there's kind of one last point I want to talk about before I talk about the excitations, and that's the issue, of course, what happens within one individual trimer. So I talked about these exchange constants that tell you about how the spins are oriented from one trimer to another as you go along C. It turns out that there is, because of a local distortion of the crystal field, there is a very small orbital degeneracy that works itself into the Hamiltonian. So there's a very small antisymmetric interaction that comes into this, and that actually fixes the orientation of the spins within a given trimer. So that gives it the structure of single-handed chiral and helical nature. And, oh, how much longer? Sorry, I lost track of time. I want to then
Almost 5 minutes.
5 more minutes? Okay, sure. So I just want to talk about, for the next 5 minutes, the spin excitations, in particular what happens in the magnetic field, and just show you some of the results that we've got. It turns out there's 2 different spin excitations you need to worry about. One is the Goldstone mode, and that's associated with basically a continuous symmetry of all the spins moving within the AB plane. That's known as the C mode. This terminology was given by Jensen. But there's also 2 transverse modes that you need to think about. These have been termed the W modes, and these are gapped at low energies. We can actually discern between these 2 excitations actually by looking at the momentum dependence. Okay, now what happens when you apply a magnetic field to this? Well, in terms of diffraction, not a lot happens. And the only thing that we can see really that goes on is that you seem to develop some sort of spin canting, which gives you this ferromagnetic moment that occurs at the break-peak positions. Now, what's more interesting actually is that if you look at the spin excitations in the applied magnetic field, this is with the field pointing along 2 different directions, one within the AB plane and then one pointing along the C-axis. And so what you see here is, okay, we put the field, it's about 12 Tesla in the AB plane, and you see you got these 2 modes that appear. Now, what's interesting is notice that if you swap the momentum transfer direction, so if you reverse the sign on Q, notice that the excitations look different. So notice that this mode comes up to about 2 millivolts. Or if you swap the sign on Q, went up to minus 0L, actually it goes up to about 3 millivolts. And you get the same effect if you do the field along C. Notice here that this is the spin excitations at 0 Tesla. And then when you put it along plus C, you kind of pull one mode down, then you push it back up. Now, one point I want to make here, and this is kind of where the terminology I personally find slightly confusing, is that if you look at this, for example, that for different crystal momentums, so if you propagate a magnon along plus direction here versus the minus, it's actually the same. So in that sense, it's reciprocal. But the effect here, you get a different answer if you change actually the total momentum transfer that you're applying to the sample. And that comes through with big Q. And that's kind of different than what's been seen in other kind of non-central symmetric magnets. This is kind of a recent paper done on copper vanadium oxide. And here actually, what they pointed out was a non-reciprocal effect. So when they swap the sign on little q, so when they propagate a magnon along plus C and minus C, or in this case it was K, what they found is that they got different answers. However, in our case, what we're seeing is that you actually need to change the direction of big Q, so the direction, effectively, of the incident neutron beam. And that's why I'm actually referring to this as dichroism. It's sort of analogous, I think, to optical experiments, where you get kind of a different answer, in this case for absorption, depending on which direction you actually transfer momentum or bring the beam along in the material. Just in terms of what the underlying mechanism is for this, what we then did was we looked at the field dependence. In particular, when you look at the field along the plus C direction, what you find is this kind of linear response. So you get a linear change with field when you put the field along the C-axis. And linear is kind of strange with magnetism because it means that somehow there's some sort of time reversal breaking thing that the magnetism is coupling to. And so that's kind of difficult to actually do just based on the chirality. Chirality obeys time reversal symmetry. So this has to be something else coming into play here. When you look at the field effect along in the AB plane, things get a bit more complicated. It turns out that at very low magnetic fields, the effect is reciprocal. So the magnons change the same way with the field, whether it's plus field or minus field. But for large magnetic fields, actually you then get back this kind of different effect where the magnons along plus, where the field along the plus direction is different than the negative direction. You can kind of see that played out in these constant Q's. So at zero field you have a little donut, and then when you go to minus field, you see one Q kind of contracts, the other kind of gets bigger, and vice versa when you swap the field along in the AB plane there. Okay, this is my last slide. In terms of what is really the underlying mechanism of this, what's interesting in all those results is that it's only this lower energy, W mode, that's affected here. And if you look at how that dispersion actually behaves, notice that it has this anti-symmetric term that kind of works its way into the analysis. And the size of this is actually controlled by spin-orbit coupling. Now, you wouldn't expect that to actually make a big difference because the spin-orbit coupling depends on two angular momentum operators, so that should obey time reversal symmetry. But remember this crystallographic structure is P321, so actually it lacks this inversion center. So you can get other terms that come into the spin-orbit coupling that are actually linear in Q, and therefore this may indeed be the origin of what the effect is here, where it's coming from. Okay, just to summarize, so hopefully I've told you a little bit about this interesting magnet and some of the properties in terms of its magnetic and crystallographic structure. And also talked a little bit about the magnons and how they behave both at zero field, but also with an applied field, and shown you this kind of interesting effect that we see that seems to actually depend on the total momentum transfer, not only the direction that you're kind of propagating it along. Okay. Anyways, thanks for your time. Thank you.
Questions? Questions about this?
So in quite a few systems that have a helical magnetic structure, if you apply a magnetic field and release it, you can induce magnetic scorions, but usually it's due to DM effect. And here you are saying the DM effect is quite small.
That's
so does it mean that there is no hope of getting a magnetic scorions in this system?
Oh, magnetic. Oh, and the static magnetic structure. So people have looked in the system, they haven't ever found them. And I think that they're probably there because there is this anti-symmetric term there. It's a lot weaker. You saw the relative numbers is 0.04 millivolts compared to 0.04 compared to 1. I think the problem is people just can't apply big enough fields to overcome that D over J, you know what I mean, term in this. So it's not like MNSI where these kind of a bigger relative energy scales. That's it. I know a lot of people have looked, but I don't know where they are. So,
Other questions from the talk, from the audience? Okay, if not, thank you.